Okay, we are going to discuss this book here. It's called Vector Calculus. It's by Susan Coley, and the table of contents looks like this, but we're only going to cover the first chapter, and actually we're only going to cover section 1, 2, 3, and 5, probably not section 4. Okay, so this is chapter 1, section 1. So there are a lot of ways to talk about vectors, and in this text there are basically two ways that they're going to use. So here they say vector is basically something like this, like 1 comma 2, or uh, something pi comma 17, something like that. So, normally we think of 1 comma 2 as a point, but we'll also use the same notation for a vector. And we can think of a vector as a point, actually, and we'll review that idea shortly. But anyway, so it's like a point, or like what we call an ordered pair. So in general, you might say A1 comma A2 instead of specifying the particular values. By the way, this is a little bit peculiar, but we could say pi is the first element and 17 is the second element, or we could say for a what we call 3D vector, um, we say pi e and the square root of 2. So when we have just two elements, we refer to that as a vector in R2. It means basically just means there's two elements, and each element in the vector is a real number. That's the R there. So these are all real numbers, right? These are real numbers. We don't have to use real numbers when we're talking about vectors, but typically we do use real numbers, and so typically we have an R, and the 2 says that there are two elements, and the 3 says that there are three elements. Okay, then they say some notation here. So they say that we're going to use bold-faced letters in this textbook. Now, if you're writing on the board, it's hard to make a bold-faced letter, but when they're typing, they can easily make something bold. So they're going to use that notation for a vector. So this vector could be called A, or this vector could be called A. Okay. They say here that, sometimes they'll use an arrow, and that's much more typical when you're writing on a board than when you're typing it in a textbook. And so vectors are bold, and if we're just talking about a number, which is also called a scalar here, a scalar, then we don't use bold. We just use something like A. So, we have to first of all say, what do we mean when two vectors are equal? And here they say that if you have a vector A and a vector B, if we call them equal, that means that not only is A1 equal to B1, but also A2 has to equal B2. So it says if A1 equals B1 and A2 equals B2. So that's what we mean by vectors. Note that if these, we don't say that two sets have to, if two sets are equal, they don't have to have that property. They just have to have the same elements. The order is not important when we're talking about sets, but when we're talking about vectors, we're going to say that the order is important. And so this has to equal this one, and this has to equal that one. And if we have three, then A1 has to equal B1, and A2 has to equal B2, and so on. So just to make that clear, they say that even though these have the same elements, this C here and D here, they have the same elements, but they're not called equal vectors. They might be called equal as sets, but they're not called equal vectors. Okay, the next thing after we decide what we mean by equal, two vectors being equal, is how about if we want to add two vectors? What do we mean by doing that? So here we call it vector addition. Suppose we have this vector and this vector, and we want to add them. In other words, we're going to do this, but we don't know what this means yet, but they're going to tell us what they mean by this. And it just means you take the first element of here times the first element of here, and so on, and you get this. For example, if you take these two and you add them, so you get 0 plus 7, 1 plus negative 2, and 3 plus 10, so you get something like this. Now, because of that definition of addition, it's not hard to show that A plus B is equal to b plus a, but you would have to show that. And also a plus b plus c here is the same as this one where you do it in a different order. Okay, we also have a vector called the zero vector, and that has the property that a plus this zero vector is equal to a. So if we want to prove that first property, that this is true, we would say, okay, let's prove it when we have three elements. Well, we're talking about R3 vectors. So a plus b, we know what that means. It means this. But because these are just numbers in between the commas, this is just a pair of numbers, pair of numbers, pair of numbers that we're adding. So we can switch the order of those, we know. So we can do that here, here, and here, but that's what this is. So we have shown that this equals that. And about that zero vector, if we're talking about R3, it's clear that this will serve the purpose of the zero vector. That is, if you take A and you add that 0, 0, 0 to A, you just get A back again because of the definition of addition. Okay. Okay, so now we've discussed something what we call adding vectors. Now we might want to discuss multiplying vectors, but that's not what we're going to do next. We are going to discuss multiplying a scalar times a vector. So just a regular number times a vector. And that is called scalar multiplication. So that is, for example, something like this. You have this vector and you want to multiply it by this number, 7. So what do we mean by that? So they tell us what they mean by that. So they say, suppose we have this vector, it's in R3, and we have k, which is just a number. I mean, this is just a number called a scalar or real number. Then the scalar product, scalar multiplication, k times a, is a vector in R3. So the result is going to be a vector in R3, and it's going to be obtained by multiplying each component of A, each component here, by the k. So we get Ka1, Ka2, Ka3. So in this case, we take this vector, we multiply it by 7. What does it mean? Multiply 7 this, 7 this, 7 that. We get 14, 0, and whatever that is, this. Okay? Okay, so once again, now that we've defined what we mean by scalar multiplication, we can say, oh, what are the implications of this definition? And so some of the implications are that if you take k plus l, so two numbers plus each other, I hope I said k plus l, k plus l, and then multiply that times a, it's the same as multiplying first k times a and then l times a. So you're allowed to do that, and we could prove that again. And then this one is also allowed. That gives you this. And then if you have k times l, so you're doing l first and then k on a, you can do kl first and then multiply, or you can even switch the order. So these are all um, uh, implications of this definition. Okay, so here, we didn't picture anything here. We just did sort of what we call algebra, but we can also try and think about geometry of vectors, but we can't do that unless we have some way to picture just a single vector. Then once we can do that, then we can talk about what happens, for example, when we multiply a vector times a scalar. What happens geometrically? We know what the scalar multiplication means, but what would happen geometrically to that vector? But first, we have to be able to just picture a vector as a geometric object. So it's probably can guess that, we said this was a vector here, for example. So probably we're going to associate this with a point geometrically, and that's going to have something to do with the representation of this vector geometrically. So it's probably not surprising that here, vectors in R2 and R3, the geometric notion So she says the fact that A is in R2 is a pair of numbers should make you think of the coordinates of a point in R2. And if A is in R3, then you should think of the coordinates of a point in R3. But she says just thinking about them as points sort of is not very interesting. So instead, we're going to think of them as arrows. So we could just think of them as points, and sometimes we do, but we can also think of them as arrows. So here's a vector in R2. Here's a vector in R3, 3 dimensions. And we have the A1 comma A2 as a point, but then we think of the vector um, like as this arrow. As I said, you could actually just also think of it as the point, but we'll typically draw an arrow. And she says 1.3, this figure down here, demonstrates that this concept, provided that we take the magnitude, we can talk about the magnitude and direction of an arrow. So the magnitude is the length, and the direction is the angle here. And here it's I guess a kind of a different angle, but a different concept of the angle. But basically, let's stick with here for now. So it's just the angle and the length. So a vector seems to have that. So if we had a different point, it could have a different angle if it was over here, and it could have a different length, right, as well. So each vector has a magnitude and a direction. And she says just one quick warning. She says there's an exception to this approach, namely the zero vector, because we did talk about the zero vector. So what are we going to say about the angle of the zero vector? That's a little bit puzzling. Doesn't really make too much sense. We do have a zero vector, so I guess we have to leave out the concept of angle for the zero vector, but any other vector will have an angle and a magnitude. I guess we could say that the zero vector, although it doesn't have an angle, it does have a magnitude, just the magnitude is 0. Okay, one thing I forgot to say was that when we have the vector here, or the vector here, A1, A2, I forgot to say that when we draw this arrow, we drew it originating from the origin up to here. So let's just read that again. All of this is fine. So she's talking about, we can think of it as this is just the algebraic approach, but we want to think about the geometric approach. She says all of this is fine, but the results of performing vector addition and scalar multiplication don't have very interesting and meaningful geometric interpretations if we just think of them as points. As we shall see, it is better to visualize vectors in R2 and R3 as arrows that begin at the origin and end at the point. Such a depiction is often referred to as the position vector of the point A1, A2, or of A1, A2, A3. Okay, so we could call it the position vector. Then she says down here, however, in physics, one doesn't demand that all vectors be represented by arrows having their beginning or their tails bound to the origin. So we don't have to start here in physics. If we're talking about vectors when we're using them in physics, we don't insist that they start here. So in other words, what's that mean? So that means here's that vector, but we're allowed to move it around. So that's because, we are talking about objects moving around, and then we want to have a vector when let's say we're talking about a ball. So, maybe it starts here and then it moves over here, but we'd still like to have a vector associated with it over here as well. It might not be the same vector as this one, or it could be, but in other words, it might not be the same direction and the same magnitude, but it could be. It could be, we're allowed to move them when we're doing physics. So physicists, I guess they want to have that ability. So it seems to work out. So she says one is free to, like, what they call parallel translate. So you take this one and you can move it over here, as long as you keep the length the same and the direction the same. So that's what they mean by parallel translate. So one is free to parallel translate vectors throughout R2. And same thing for R3 if your vector is an R3 vector. So that is, one may represent the vector A1, A2, A3 by an arrow with its tail at the origin and its head here, or with its tail, the base, at any other point, so long as the length and the sense of the arrow, that means the angle, are not changed. For example, if we wish to represent A by an arrow with its tail starting here, do they show us that? So here we had, I guess, this A, but now we can also move it so that the origin of this A is not here, but starts over here, but it still points in the same direction and has the same length. So, for example, if we wish to represent A by an arrow with its tail starting here, then the head of the arrow, where would it be? It will be, we add the A1 to X1, we add the A2 to the X2. So we're starting here, and we want to know where the tip is now, and the tip is going to be, in other words, where's the point going to be? I guess it's going to be here, here, here. So if we start here and we add A to it, or we draw A from here, then we end up with the tip being over here. Okay, so now we sort of have this concept of the geometric understanding of a vector. So, we started out with just the algebraic. We didn't have any picture. We didn't draw any blue. Nothing. We didn't have three space. We didn't talk about that. We just talked about a vector called, A1, A2, A3, period. There was no picture of it. Okay, but then we introduced this idea of the picture of it, or the geometrical perspective. Okay, now remember though that we had talked about adding two vectors. So what does it mean geometrically when we add two vectors? So that's what we might want to think about. So she says, with this geometric description of vectors, vector addition can be visualized in two ways, actually. So the first one is called the head-to-tail method for adding vectors. So here it is. So here's a vector A and a vector B. Remember, now we're thinking of them as geometric objects, these blue arrows, in other words. But before we were just talking about them as over here. Here we're talking about adding two vectors, but they weren't geometric vectors. They were just like pairs of numbers, and we were adding the pairs. But now we have this geometric view, and we can wonder what happens when we add two vectors this way. Well, obviously we get a new vector when we do that. In fact, here, which is kind of I don't like this example because it's kind of confusing, right? You use pi and the square root of 2 as the coordinates of the vector. Well, I don't know why we have to introduce that sort of confusion into this basic, they're introducing addition. Why do they have to add this confusion to it? Why don't they just say 1, 1 plus 2, comma 3? But anyway, they're doing this. So it's 1, 1 plus this. So it's 1 plus pi there, and 1 plus square root of 2 here. But what if we try to picture so first of all, when we add two vectors, we get a new vector. And then, so what does this new vector look like? So if we want to picture addition, what does it look like? Well, remember that we're allowed to sort of move these vectors anywhere we want, right? That's what we said, parallel, I forgot what they said, but parallel something, right? We're allowed to move them around. Parallel translate, we're allowed to move them around wherever we want. So that might help us a little bit in sort of understanding what it means to add two vectors geometrically. We know how to do it so-called algebraically, but what about geometrically? So here's what happens. We can we hope that when we add two vectors, we get a new vector. We said that. So what does the new vector look like? Well, we just said that we're allowed to parallel translate. So we have one vector A. Let's say both vectors B, A and B. Suppose we show them initially at the origin. Now they don't do that here, but we could have two vectors, A and B, and they're both drawn with their tails at the origin at first. But we want to show this way what it means to add those two. And one way to understand what it is to take the first one and draw it. It doesn't even have to be at the origin. And then we're allowed to move the other one around, B, all anywhere. So what we're going to do is we're going to move it to here, where the tail is here, and then the tip will be somewhere, in this case here. And so what will the result be? Well, it turns out that it's going to be the vector that's drawn from here to here. Now, what does it mean it turns out? According to the definition of addition that we gave up above. So we have to show that it turns out that that's what it looks like geometrically. Because here we gave the definition, here we gave the definition. That definition implies that this little drawing makes sense or works. But we have to prove that, really. So she says we still should check that these geometric constructions like this will work. Will agree with our algebraic definition. For simplicity, will work in R2. So we'll just use vectors in R2. So here are two of them. And we want to somehow show that this is, when we do the addition like this, that we actually, that this sort of visualizes that. Okay, but let's just jump right to the parallelogram law, which is another way to visualize the addition of two vectors. So let's just see what that looks like. So you can put the tails of the two vectors together and still visualize what the resulting sum will be. And you can do it like this, and this will be the sum. So this is called the parallelogram, because that parallelogram rule, because this is a parallelogram. So you can do it that way. And then the next thing is, so we talked about visualizing the sum of two vectors. The next thing we want to think about is visualizing the product of a scalar with a vector. So remember that we can take a scalar and multiply it times a vector like this, k times a. And the question is, what does the result look like? We know how to calculate this, but we just multiply each element in a by k. But what does it look like? And the answer is that if you take a and you multiply it twice by 2 rather, then you get a vector which is twice as long, but in the same direction. So the point is that it doesn't change the direction, but it will change the magnitude of the length. And if you multiply by a negative scalar, it will flip it to the opposite direction and can change the length as well. Okay, now notice that we never defined subtraction of two vectors, but we can define subtraction now in terms of the operations that we already have, which are addition of vectors and scalar multiplication. So they say that if you want to define a minus b, you can just say, well, it's just a plus minus b. And by minus b, now we know that it's the negative 1 times b. So with the operations that we already have, we can define how to subtract two vectors. Now, the visualization of this always confuses me, or used to always confuse me, because, okay, so a minus b, we just said we know what it means. It means a plus minus b, and we know what adding two vectors is, and we know what multiplying b by a negative is. So we know what that is. So we know what A minus B is. But what does it look like? Well, first of all, it's going to be a vector. Of course, when you add two vectors, you're going to get a new vector. So it is a new vector. The question is, where is it? Okay, so the picture here shows us where A minus B is in terms of A and B, and it looks wrong because A minus B, they call it C here, is this vector. So where does it go? It goes from B to A. It seems like it should go from A to B. At least that's what I usually feel, but that's not right, and you can easily verify it by checking if we add this to B. Well, we see what happens if we add this to B. We should get A. And so, whereas I think it should be going in this direction, so that would say that if we add this A minus B to A, we should get B. But which one is correct? When we add B and C, that means we're adding B and A minus B. So you can see that the B's cancel out and you get A, which is what you're supposed to get. So it's, and then if you try it the other way, you don't get B. So if you take A and A minus B, you get what? 2A minus B, which is not B. So it is correct that it goes from B to A, not from A to B. So anyway, the question is, what does A minus B look like? And the answer is, it's the vector which goes from the tip of B to the tip of A. Okay, so the next thing they do is they define, this is a definition, something called the displacement vector. So what do they mean by that? So in this picture, you can see that, well, anyway, what do they say? They're talking about given 2 points. Now remember that points can sort of represent vectors, right? So like here's the point P1, and it supposedly it's up here, but we know that that's like a vector that points to P1 as well. We can also think of it as a vector. But here they're talking about it in terms of points. And that's the point of this definition. But so what does it say? It says if you have the point P1 and the point P2, the so-called displacement vector from P1 to P2. So, this is really what we just called this vector minus this vector, right? We just talked about A minus B being the vector that goes from B to A. So this is this one. So this one goes from here to here. So it's this one minus this one. But we're not, in this particular definition, they're not thinking of this vector, they're thinking of this point. And they're not thinking of this vector, they're thinking of this point. But you can see that it's more or less the same thing. Anyway, but what the displacement vector from this point to this point is, we can see that it's the same thing as this dashed vector minus this dashed vector. Just like this was just like this was A minus B, this is this vector minus this vector. So what is this vector? It's P2. So it's this, x2, y2, z2. And what is this vector? It's P1. It's x1, y1, z1. So what's the difference between this vector? Remember, I'm saying this vector, I mean like without that P2 there. It's just the vector. Here, this means the point. And the difference is not really that important, but it's just we're trying to define the distance between 2 points as a so-called displacement vector. It's really just terminology. Anyway, what is it? It's x2 minus x1, y2 minus y1, z2 minus z1, and that's what they have here. So this vector, we know that it's one thing we can call it is this minus that, but another thing we can call it is the displacement vector from P1 to P2. So it's really no different. It's just focusing on the fact that we're talking about points here instead of vectors. Okay, so let's take a quick example of some of this. So we say, suppose we have like a particle in space that's located here. So when we say that it's located here, we can say, oh, well, these are the coordinates of it. Or we can say that it's identified by the vector A, which has, the same specification here. Sometimes we call it point, sometimes we call it a vector. Doesn't really matter. But anyway, so we could we could have a point here, and we could say that, or a particle rather, and we can say that it's moving in space. And let's suppose that we want to say that it's moving in this direction, and it's moving at a certain constant velocity. Okay, so we can imagine such a situation. There's a point, particle rather, it's moving in space, and it's moving at a constant velocity, and we say, okay, it starts here, and it's moving in this direction. Now we can use a vector. Besides saying we can use a vector to identify its initial location, we can also use a vector to identify its so-called constant velocity, because velocity, actually, maybe we don't normally think of it that way. We sort of think of velocity and speed as the same word, but in certain uh, fields, when we say velocity, we mean not only the speed, but the direction. So let's take the word velocity to mean that. So then it has a certain direction, which we already said it's going in this direction. But since it has a speed or a magnitude and a direction, that sort of reminds us of something. It reminds us of a vector. So maybe we can use a vector to indicate its speed and its direction. And yeah, of course we can, because that's exactly what a vector does. It indicates not its speed, but it indicates its a magnitude and a direction. And so what we'll mean by the magnitude in this case is the speed. We'll use the magnitude of the length of the vector to indicate the speed. So if we wanted to say it's going faster, we'd have a longer vector. That sounds a little bit strange because we tend to think of this as like kind of in the physical space, but that's not really what it is. It's just something to indicate the speed. So it's not exactly like we imagine it in the physical space. It's just a tool for us to indicate the speed. So anyway, this has a certain speed, so we're going to draw a vector. Um, the length of of that vector is going to indicate the speed. So if we only drew it half as long, we'd be saying it wasn't going as fast. And remember, it's a constant speed, so it's always going the same speed. Okay, so anyway, and then it also has a direction, of course. When it's moving, it has a direction. So it's perfectly fits the use of vectors. And why is that? Because this is why people developed the concept of a vector was for this kind of scenario, actually. So of course it's going to fit very nicely. Okay, so we can say that at first the particle is here. In fact, we did say that at first the particle is here, and then it's moving. So, what we're going to say is we're going to let t equal the number of seconds, and we're going to say that the velocity is given in the number of seconds. And you might say, now, why are there three elements in the velocity? What's that about? But we can break up the velocity into its so-called x component, y component, and z component. So we say, okay, well, it's moving a certain it's moving a certain amount in the x direction, maybe it's in the negative x direction, and it's moving a certain amount in the y direction, maybe it's moving in the negative y direction, and it's moving a certain amount in the z direction. So right, we can think of velocity that way. It has a kind of x component, a y component, and a z component. So we're going to specify those components with v. And so v will be perfectly reflection of that velocity. Okay, and we're saying this is the velocity. It's moving at a constant velocity, and so we can say after 1 second, it's moved a certain amount. After 2 seconds, it's moved like double that, and so on. So it's moving in this direction, but this can be written as I just said, having a component in the x, y, and z direction, and that's what this is about. And then uh, So, okay, so where is it? Where is it? Well, when t equals 0, it's right here. And then when t equals 1, if this represents the velocity, so it's moved to here. And then after at t equals 2, it's moved twice as far, and when t equals 3, it's moved after that. So we can say, so where is it? Well, it starts out here, so we can say this is the initial position, this represented by this vector, not by this point. We can also say by this point, but I want to use the vector view of things. So I'd say represented by this vector, and then what do? We add the velocity vector to that. And we add t times the velocity vector because we want to let it depend on t. So we get a plus tv, which is what we have here. Okay, so this represents, so what do they say? Then the particle's displacement from its original position is tv, and its new coordinate position is ATV. So where is it after 1 second? It's here, which is what? A plus V. Where is it after 2 seconds? A plus 2V, and so on. So in general, it's A plus TV. And then they just make this concrete by saying, suppose you have a spaceship, so it's a spaceship now, and its initial position is here, and it's traveling with a velocity of here. So these are the components in the x, y, and z directions. And so it means it's traveling 7 miles per second, for example, in the positive x direction, 10 miles per second in the negative y direction, and 25 miles per second in the positive z direction. So that's what these mean. Okay, and then so we just mimic what we have here. So we say the initial location, which we can say the initial vector, plus 20, or 20 means for 20 seconds. Suppose they're asking where is it after 20 seconds. So 20 times v, this is the v. So we can just do this calculation. This is not hard. We just have that, and then 20 times each of these. Then we add these, and we get that. And that is the displacement from the initial position after 20 seconds is here. Okay, let's move on to the section 2 here. It's called More About Vectors. And suppose we just have the xy plane. And of course, we can draw all kinds of vectors in here. But we want to just single out two sort of very important, the most important vectors maybe, and maybe the simplest vectors as well. So these are two vectors, and they're simple in the sense that this is only in the x direction, and this is only in the y direction. So and let's suppose that this is of length 1, and this is also of length 1. So these are called unit vectors because of their length. Length 1, length 1. Any vector that has a length 1 would be called a unit vector, but these are unit vectors. But these are special unit vectors because this one only points in the x direction, this one only points in the y direction. Now, of course, everybody knows that if you have a point up here, you can say, well, to get there, how much do you have to walk in this direction? And then how much do you have to walk in this direction? That is, we can say that, and we can express that as the amount you have to walk in this direction is a vector, and then the amount you have to walk in this direction is a vector, and then by the way that we defined the sum of two vectors and the way that we visualize the sum of two vectors, then we, to get this vector just means you take this vector plus this vector. That's exactly the way we define the sum of two vectors, at least geometrically. So, okay, so we can say that any vector A, we say has a kind of a component in this direction and a component in this direction. And we say that we can write any vector A as a, A has some coordinates, right? In fact, the coordinates are what? A1, A2. It's the amount you have to go in this direction and then the amount you have to go in this direction. That gives you the two coordinates. And then, but you can see also that because of the way we define vector sums, that A is equal to A1 times the unit vector in this direction. The I might only go to here, but maybe we have to go double I. So it would be like 2 I, or in other words, the coordinate would be 2. And then we'd have to go maybe 3 units in the j direction, for example. So that would be 3j. So the coordinates just get sort of pasted right as coefficients into this expression, and that gives us A. Now we can also do this just algebraically instead of thinking about it geometrically. Here we're looking at it geometrically, and it makes perfect sense when we have these two unit vectors. By the way, these two unit vectors have a name. They're called the standard basis vectors. Now, if we want to talk about 3 dimensions, we also can do that. We can have, again, the x direction and the y direction. That's the same x and y. And we have I and j as the 2 unit vectors in those 2 directions. And then we can have another one in the z direction. That's called k, usually. So we can have I, j, and k. But just going back to this situation, not 3 dimensions, just 2. And this is the way, so we see that this A vector, or this point A, so to speak, can be written like this, as the sum of the coordinates of A. I didn't write that here. I guess it's written up here. What is A? Here's A is A1, A2. So I didn't mention that, but A, the coordinates of it are A1, A2, or the vector expression of it is bracket A1, comma A2, close bracket. So anyway, once, if we have A, we can write it like this is what we wanted to say. And we did all of that just visually, but we can also do it algebraically. So if we go back up to here, so here's A1, A2, and then it's obvious that this is true. That is, if I add these two, what do I get? I get this. And if I add this to that, I get A1. If I add this to that, I get A2. This is obviously true, that the right-hand side equals the left-hand side. But then I can factor out the A1 out of here, and I get this. Oh, I'm sorry, I forgot to say, what are the coordinates of this, of I? So the coordinates of I are, we go 1 unit in the x direction, so it's 1, comma, 0. We don't go any units in the y direction. So the coordinates of this are 1, comma, 0, or we can say the vector is 1, comma, 0. And how about this one? This is j is 0, comma, 1. So, okay. So I is 1, comma, 0, and j is 0, comma, 1. Okay, going back to here, this obviously equals this, but I can factor out the A1 here from here. So what do I get? I get 1, comma, 0 times A1 gives me this. And here, if I factor out the A2, what do I get? A2, 0, 1. But these are what? This is I is 1, 0, 1, 0, I. So this is A1I plus A2J. So we have that. But that's what I said. I said we did this geometrically, but we can also do it algebraically. So in both cases, we see that A1, A2 can be written as the sum of this piece and this piece. This piece has I, and this piece has j. So we can say that any vector A1, A2 can be broken up into the sum of basically 2 standard basis vectors. These are the 2 standard basis vectors. So it can be broken up into sort of a constant A1 times the first standard basis vector, which is I, plus a constant times j, which is the second standard basis vector. So any vector can be broken up this way. And this is like very simple to break it up. I mean, I'm saying it's going to be something times I and something times j. And what are those somethings? It's just these. So it's kind of very simple to go from here to here. And if you're in R3, you can do the same kind of thing. Okay, so in R3 you can take A and write it as A1I plus A2J plus A3K. So this vector can be written as the sum of basically some kind of multiple of I plus some kind of multiple of J plus some kind of multiple of K. And the some kind of multiple, the things that are multiplying it, are precisely the coordinates of A. Now, I shouldn't really use the word coordinates, or I don't think we've defined it that way, but everyone knows what I'm talking about when I say the coordinates of A. I guess I should say maybe the components of A, because A is a vector, it's not a point. So maybe I shouldn't use the word for here, the coordinates of A, because that means it's a point, but we're thinking of it as a vector, so maybe I should say the components of A instead. But I think we know that it's sort of the same thing, just we're calling it a vector or we're calling it a point. So she says here, let's see, what does she say? Oh, she says that we can write the vector with its sort of component, in its component version here, or we can write it like this. And we should just sort of get used to being able to flip from here to here and from here to here. So she says, where does she say it? She says, here, she says, it's your choice which notation to use. So either the component form or this form, as long as you're consistent. You don't even have to be consistent, but if you're doing like some math with it, you have to be consistent. But the IJ notation is generally useful, this notation here, for emphasizing the vector nature of A, while the coordinate notation is more useful for emphasizing the point nature of A, in the sense of A's role as a possible position vector of a point. Okay, geometrically, the significance of the standard basis vectors, these things, or these things, geometrically, the significance of the standard basis vectors I and J is that an arbitrary vector A can be decomposed pictorially into appropriate vector components along the x and y axes, as shown in figure 1.8. So we did that already. We already said that we can do this. Okay. And then for the I, J, and K, now, you might say, oh, well, look, this is the same I as this I, and this is the same J as this J. And that's true, but now we're thinking of things in 3 dimensions, so we have to give each of these a third component. So we can't just call it 1, 0 and 0, 1. We have to have a third component. So we have to call I 1, 0, 0. So what does that mean? It goes 1 unit in the x direction, no units, 0 units in the y direction, and 0 units in the k direction. So it's 1, 0, 0. And then for j, we have to say it's 0 units in the x direction, but 1 unit in the y direction, but 0 units in the k direction. So that's 0, 1, 0, and then k is 0, 0, 1. So we can do that. And we can say that a vector in 3 space, which is written like this, can also be written like this. And again, you should just be able to switch from this way of expressing a vector to this way of expressing the vector. So like here we have this vector, but we can also write it like this. There's 1 times I plus negative 2 times j. And here we have this vector, and we should just be able to switch and write it like this. And you just have to be able to go back and forth like that. Okay, so now we're going to go to something called parametric equations. So here is a circle, and I think no, it's not a unit circle. It's not supposed to be a unit circle, but we can't tell that here actually. Um, could be a unit circle. It might not be a unit circle because they didn't tell us what the coordinates of this point are, so we don't know. Okay, now, but they have these t's floating around here, and we don't know what's going on about that. But we could sort of imagine that like we had an ant, and it was crawling around, and this is where it was when t equals 0, and then when t was something else, it moved up to here. Forget about this particular crazy-looking number, but just when t was somewhere else, it got to here, and then when t equals something else, it got to here, and when t went to something else, it got to here, and then it came back again to the beginning. So that's kind of what we could think of as t. In fact, the fact that it's t is suggestive that it's probably having to do with time, although they're using kind of weird, I mean, this is not exactly the way we would talk about time. Time is like 1 second, 2 seconds. This is certainly not that kind of number. But anyway, we won't worry about that. Anyway, this is a circle. Now, of course, most of us know what the equation of a circle is. For example, if this was a circle of radius 2, so this length was 2, then I think most of us know that the equation for this is x squared plus y squared equals 4, right? So you get x squared plus y squared equals 4 over here, and that will define a circle of radius 2, right? This is the square of the radius, so the radius is actually 2. Okay, so that's just something I just wanted to mention about this picture here. Okay, like I said, we want to talk about this, parametric equations of lines. Okay, now, of course, we know exactly what we mean by the equation of a line. We know that so y equals mx plus b is the way we write the equation of a line, at least in R2. So she says in R2 we know that the equations of the form y equals mx plus b, or of course we could rewrite it like this, ax plus b equals c, because we could just bring the mx over to this side and then I guess divide by, well, no, we don't have to divide by anything. So anyway, but in general, we can write it as ax plus by equals c. That's another way to write the equation of a line. And they describe straight lines. So she says, consequently, one might expect the same sort of equation to define a line in R3 as well. Consideration of a simple example or two, such as figure 1.21, should convince you that a single such linear equation describes a plane, not a line. So I guess she says, here's a y equals 3. This defines a line. But if we take y equals 3 and we use that in 3 dimensions, so here, y equals 3, we don't get a line anymore. We get a plane. Because, when we say y equals 3, we mean we don't care what x is, always y is equal to 3. This equation doesn't have an x in it, so we can say that y is not dependent on x. It's just always the same thing. It's always 3. So we get this horizontal line. So we can think about this the same way. We can say y equals 3. What does that give us in the x, y, z plane in 3 dimensions? So we're just saying y has to equal 3. We don't care. Whatever x and z are, y will equal 3. So if I take this x and this z, then y equals 3. So we come out to here. And if I take a different x, like this x, and this z, still we come out to 3. So what does this form, y equals 3? In this case, it forms a plane, whereas here it forms a line. So we probably shouldn't expect that if this gives us a line, if this gives us a line in 2 space, that it's probably not, or this one gives us a line in 2 space also, that it's probably not going to give us a line if we just do this, but we're talking about in 3 space. So this probably also, either of these, also define a plane in 3 space. So she says it describes a plane, not a line. And then she says a pair of 2 simultaneous equations in x, y, and z is required to define a line. So just having one equation in x, y, and z, just like here we had one equation in x and y, gave us a line, but to get something for a line, what we're going to need is 2 equations in x, y, and z. So you can think of that as if you have one equation in x, y, and z, you get a plane. And if you have another equation in x, y, and z, you get another plane. And when you have them as simultaneous equations, meaning you want solution to both of them, chances are you can imagine like this is one plane, and then you have another plane sort of somewhere else, and those 2 planes are going to intersect in a line. So that's the way that you can get pinpoint a line, is by giving 2 equations in x, y, and z. One equation in x, y, and z gives a plane, so 2 will probably intersect, and the intersection will be a line, so the 2 together simultaneously will specify a line. So she says we're not going to discuss equations for planes right now. She says we're not going to do it until section 1.5. And she says here we're going to concentrate on using vectors to give equations for lines. So we're not going to do this. We're not going to talk about planes right now. So somehow we're going to use vectors maybe to get an equation for a line in R2 or R3. And then she says this other thing about parametric equations for lines. She hasn't explained that yet, but we'll see the kind of a second way of getting equations for a line, besides using vectors, this other way. But we have to wait and see that.